Okay, today continuing on, and let's wrap up the logic design circuits and the gates. All right, 17 and logic inverter. All right, so we had stopped here. This was an implementation of a logic inverter, meaning a NOT gate, using pull-up resistors. This can be implemented using pull-up resistors or pull-down resistors, right? This is the output of a NOT gate or an inverter gate, as the name suggests, is inversion of the input voltage. If the input is low, the output goes high. If the input is high, output goes low. So, any questions about the operation? Okay. All right, then let's look at the two-input NAND gate. NAND, as the name suggests, is a combination of the NOT and AND gates. AND gates, or logical AND, is similar to arithmetic multiplication. So 0 and 1 gives us, for an AND gate, 0 and 1 gives us 0, 1 and 0 gives us 0. 1 and 1 is the only input that gives us a high output. NAND gate is the exact opposite. So NAND gate, the output's high for all inputs except when both inputs are high. Okay, so the output of a NAND gate goes low when both inputs are high. And that's what we see here. So in terms of logic or binary numbers, you have already seen this before, right? In 133, right? The NAND gates and the operation. This is a look behind the curtains, meaning if you wish to implement this using circuits, that's how this would work. So this would require two switches because a NAND gate is a two-input gate, right? Except for the NOT gate, which is single input. All the other gates are at least a minimum of two inputs. So it uses two of the four switches inside the CD4066 chip. Okay, so it's half of the CD46 chip, 4066 chip. All right, inputs are A and B. And then you have a pull-up resistor, 10K, where the output is always connected to the 10-volt high line. So the only time the output would be connected to ground is when both switches are on, right? This is simply by observation. This is simply by inspection. If we inspect the circuit diagram, we can see the output is connected to 10 volts via the 10K resistor. And then the only time it can be connected to ground is when both switches are on. The only way for both switches to be on is for A and B for both inputs to go high, meaning connected to 10 volts. So if we use that, when VA, either VA or VB are 0, one of these switches will remain open, right? In order for the 4066 switch to function, we need to apply a high input. You apply a high input, the switch activates and it closes. For all other inputs, switch is going to remain open. So if VA, let's say, VA is 0, but VB is 10, your output is still connected to plus 10 volts, right? There's no connection to ground. If VB is 0 and if VA is 10, your output is still connected to plus 10 volts, right? So if A or B, either one of them is on, sorry, if either one of them is off, then the output is going to remain high. Does everyone see that? The only time it can go low is when both are on, and this gives us the on resistance of both switches. Okay, so output is now connected to ground, but we must take into account the on resistance of the switch. Okay, if you want to calculate the voltage or the current, take that into account. Go back to the spec sheet. Our spec sheet states the on resistance for an applied VDD of 10 volts is between 180 and 400 ohms. So if you pick the highest, which is 400 ohms, right here, and then we get an approximate output voltage of 0.9 volts. Okay, 0.9 volts. Because it creates a voltage divider network with a 10 kilo ohm resistor. All right, let's take a pause. Let me know if you have any questions. Yes. The question being asked is, if we use a pull down resistor instead of a pull up, would this become a NOR gate? OR gate, OR? Okay, OR. Let's see. I don't know. I'd have to sit and analyze, but that's a good question. Hold on, sorry. It's coming up in about 2 slides. So let's get this one done first, and then we'll answer that question in the last slide. Okay. Any other questions? Does the step, do the steps make sense? How to apply the analysis steps and how to calculate the circuits, right? The truth tables and everything was one way of looking at it, but if you're training to be a computer engineer where you're learning about the circuits and hardware, then you need to be able to understand how to calculate the voltages and currents that will be present in that circuit. And so that's what we do in these analysis techniques. Okay, so let's tackle the next one. Here we have both switches connected in parallel. So let's do this together. All right. Let's say, so this is a pull up resistor. So let's draw that first, 10 volts. And then this is our output, right? Let's say VA, so we have our truth table. We have 0, 0, 0, 1, 1, 0, and 1, 1, right? So VA is 0. Is the switch open or closed? A is open because A is 0. How about B? Sorry, for this case, if B is 1, is my switch open or closed? So what is my output? Output is 0. Because now has a direct pathway to go to ground, right? So output is 0. So for 0, 0, for this is 1. Sorry, not 1. 0. And by extension, we can automatically deduce what would happen if A is 1 and B is 0. Output now has a pathway to ground via A. So output is again 0 volts. And so what this tells us is, if either one of the switch is activated, meaning it's closed, it provides a pathway to ground. And if it provides a pathway to ground, that means the output is 0. So if both switches are open, nothing changes. It still provides a pathway to ground. Output still is 0. So let's take a pause while you look at it. Think over what happens when both inputs are 0. All right, once you finish writing that, tell me what happens when both inputs are 0. Anyone? Yep. Both switches are 0. That means there's no pathway to ground. So output is equal to 10 volts. It's connected to the 10 volt line by the pull-up resistor. And so output should be, well, not high, but we need to calculate. We need to calculate. V out is 1, but actual V out voltage would be, what would it be? It's 10 volts. Because there's nothing to actually, there's no current draining that's going on in there. But what you need to calculate is the drain resistance when the switch is closed. So if the switch is closed, then it forms a voltage divider network. So for both these cases, we have a 10 kilo ohm resistor. When only one of the inputs is activated, oh sorry, when one of the inputs is high, then you have a single R on, meaning the turn on resistance for the switch, right? CD4066 for a 10 volt input has a resistance that is between 200 to 400 ohms. So let's assume 400 ohms. If you assume 400 ohms, it's going to look like this. Or VA equals 10 volts or VB equals 10 volts. If both VA and VB are 10 volts, what changes in the circuit? If both VA and VB are activated, you already know the answer is low, but what actually happens in the circuit? Current flows through the two switches. So what does it mean in terms of resistance? Both switches are activated. Exactly. So you have turn on resistance for both switches, and they'd both be in parallel. And so now your effective resistance is half. And so this then becomes, if R on is, let's say, if you assume 400, this R on would be equal to R on divided by 2. So approximately equal to 200 ohms. Output voltage would now be slightly less, or actually half of what it was for the first one. Okay. So again, when a single switch is on, you have one single drain, switch resistance. When both switches are on, then you have two of them in parallel. And so effective resistance, REQ, is divided in half. Does that make sense? Any questions? Yes. So question being asked is, when they're both open like this, and there's a direct pathway from output to go over there, why is there no voltage drop across the resistor? Because as far as we know, there's nothing else connected to the output. And so at the output is open, we are simply measuring the output. That means there's no other circuit connection at that point. So there's no current flowing through there. We are simply calculating, right? We're simply measuring. So it's as if we had a power supply and we connected a resistor to one end of the power supply, but the other end is not connected to anything. So yeah, there's no current flowing through there. Good question. Any other questions? Okay, so when it's both are 0, 0, you already calculated that the on resistance is high. What is the output? The out is 1. So what kind of gate is this? I'll leave you to think over that and answer, because we only have 2 minutes left. So I want to finish up this next one. If we switch this to a pull down resistor, what happens? That was the question that was asked earlier, right? If you switch the pull up resistor to a pull down resistor, then what happens? All right, let's draw it out. So if VB is 0 and VA is 1, actually, let's do the other way around, since the truth table is like that. So VB is 1 and then VA is 1. So if VB is 1, we short this, but VA remains open. Your output is here. So if VA is 0 and VB is 1, output is equal to what? Is the output pulled up to plus 10, or is it pulled down to the ground? It's pulled down. So output is logic 0. By extension, these two cases will be the same, right? So it doesn't matter whether a switch is open or not. If the other one is open, then output is automatically connected to ground, so it's 0, right? So this is VB equal to 0 and VA is equal to 1. So if either one of the switches is open, output's already connected to ground, right? So it doesn't matter which one it is. And the only case output is connected to 10 volts is if both switches are closed. That means both switches must be activated. This is VB equal to 1, and this is VA. This is R. This is VA is equal to 1. This is the only case where output also is logic 1. Okay, for all other cases, output's always 0. So output goes high only when both inputs are high. For all other cases, it's 0. What kind of gate is this? I heard someone say OR gate. There was one word for OR. And NAND. Anyone with a NAND? All right, let's see. 0 plus 0 is 0. 0 plus 1 is 0, so that's not an OR. 0 times 0 and 1 is 0. 1 and 0 is 0, and 1 and 1 is 1. So verdict is that this is an AND gate. All right. So I just want to make sure everybody understands. We're going to end here today. This is the last slide, but I'm here to answer any questions if anybody has. All right. Okay, we'll end class here and I will see you all on Wednesday.